All right. Are there any questions? Then let's pick up where we left off. Box on ramp. And for the sake of making this slightly simpler, I'm going to make the ramp is part of the ground. So if you need a visual, somebody has created a ramp out of dirt. And the traditional symbol to indicate that this is fixed. All right, we're doing the force diagram. So the question is, what is the first step?
Separate.
All right. I don't have to draw them so that they're oriented in the same orientation as here, box is above the ramp, and I draw it here. I just find it personally easier to do it that way. I also recommend drawing the box at the angle. So try to draw it in basically the same orientation as the box is in the problem. Some people do not do that. It's not inherently wrong, but the students who sort of straighten out the box, there's a mistake that is coming up that they tend to make. Let's put down our checklist. All right, so can we eliminate anything?
There is no any.
Sorry,
There is no any force like tension or other.
All right, so tension and other are out.
Just weight.
All right, let's just do one at a time. All right, so there is weight. Which way is weight acting on what? Okay, is there weight?
It'd be gravity down on the box. And then up from the ramp.
All right, technically it's from the ground. Now, whether you draw it over here or wherever you draw it, since the ramp is part of the ground, that's fine. If the ramp were separate, and the reason why I'm picking on that one, if the ramp actually were not attached to the ground or part of the ground, then the weight would not be up on the ramp, it would be up on the ground. All right, so we have only one object besides the planet, so only one weight, so weight is done.
There is a normal force.
Right, okay, so both of those exist. Let's do normal first, and then let's get friction, since friction's the new one here. Which way is normal force acting on the box?
There is a friction.
Up on the box.
So up. What does normal mean?
Perpendicular.
Yes. So perpendicular to what?
Surface of contact.
Yes, and what's the angle of the surfaces of contact? All right,
90 degrees.
90 degrees?
The box on the ground.
So where are the surfaces of contact here? Is it like this, or somewhere in between? It's diagonal. So perpendicular to that is that way. The force on the box is in that direction. So rookie mistake, whatever we're up to. There are a lot of people who always want to have normal force opposite of weight, and no, it's not always opposite of weight. Matter of fact, there's a situation where normal force and weight are in the same direction. Ooh. Here's an example where normal force and weight are in the same direction. We'll take this pen right here. All right, ready? I was pushing down on the marker. That was a normal force. Weight was also acting down because of the planet. So weight and normal force were in the same direction. But here, normal force is at a jaunty tilt. Okay, questions about why the normal force is this, in this direction? All right, forces come in pairs. Where's the other normal force vector?
Down on the slope.
Okay. And now, friction. Friction opposes desired relative motion. So, relative to the ramp, which ways does the box want to go?
Downwards.
And therefore, friction acts which way on the box? In the same direction?
No, opposite.
Opposite, it opposes. So friction is acting this way. Friction's trying to stop it, slow it down at least. And then this way, and then down the ramp. Questions to hear? So normal force done, friction done. Yet one more force diagram under the belt. All right, so we're going to go through a similar one, except now we're going to detach the ramp from the ground for a visual. So I'm going to get my hands on the right piece quickly. There we go. Imagine this table is the Earth. Put it that way. So this is what we're dealing with right here. So box on ramp that is not attached to the ground. So now I have two objects besides the planet. So flashback to box on ground, except now we've got a ramp. So box on ramp on ground. Separating, first thing, so let me draw my box. Let me draw my ramp. And let me draw the ground. Let's put up our checklist. Can we eliminate anything? Yep. Just as before. All right, I still think weight is the easiest one, so let's start out with weight. Weight is acting on what object in what direction?
The ramp to the ground, or sorry, yeah, the ramp to the ground.
Ramp to the ground? I'm gonna take you literally what you just said.
Oh,
What do you mean?
so from the middle of the ramp down to the ground,
Middle of the ramp, down,
to the ground. Right. Down
Right.
on the ground.
down on the ground.
Yes.
That's what you mean.
On the ramp,
Down on the ramp.
yes.
Okay, down on the ramp, that I'll buy.
That's the.
That's what I was trying to say.
Now, I understand that the way you're saying it right now is not necessarily the way you would do it on a test, so, but just trying to work on the language here. How should I label this?
W. One.
Weight one, okay. Personally, I would go to weight sub R just because of ramp, but the weight sub one works, and that's what was spoken. All right, so they come in pairs. Where's the other one?
Up on the ground.
Yep, up on the ground. If doing this to perfection, these two arrows should be the exact same length, but opposite directions. All right, so what else?
Weight on the box going downwards,
Yep,
and then another weight going up on the ground.
W good, or do you want a subscript?
Probably B for box.
B for box. Whatever the subscript you use is, just as long as it's different than what you're doing for the weight of the ramp. And again, for the perfectionists in the group, if the box weighs more than the ramp, then this W sub B should be longer than W sub 1. If it's not as heavy, it should be smaller than W sub 1. Now, in the complex force diagram problem, I don't give you that level of information, so just drawing an arrow downwards works. So that's, I just have two objects other than the planet, so, and I have my two weights there, so weight is done. And while I'm thinking about it. And what now?
There is a normal force between the triangle and the ground.
Okay, which way is it acting on the triangle?
The arrow from the triangle go up, and the ground go down. Then Y1, in the ground Y1.
Okay.
And then there are normal force between the square and the triangle. The arrow in the triangle go down. Yes. Why?
Remember, it's perpendicular to the surface of contact.
Go by angle.
All right.
Y2, then from the square by angle Y1.
Going which way?
Go down, go up.
Oh, okay. And you said 2. Yeah, it should be the same as what we had right there. Same direction, just slightly different label. All right, so normal force happens wherever there's contact between two surfaces. And so I have two surfaces there, got my normal force, two surfaces there touching, got my normal force, we're done. Despite what some students will claim, there is no normal force between the box and the ground. All right, friction.
So where's the first one? Did you say was the first one?
Okay, so I have one going up this way. And then down the ramp that way.
We wouldn't have with the ramp on the ground, right?
Why not?
Because it's not moving, like.
All right, so let's go to our just incredibly fancy look right here. I will do it over here. For those who are watching this later, this is going to be a perfect demonstration. All right, so imagine this is heavier, so I'm going to sort of add additional weight from my hand. Or probably even better if I'd done it that way.
Friction that way, on the right, or on the right,
On the right, friction's going that way.
or on the ground friction's going. I'm trying to think of ways.
All right, so as the box falls, if this were a frictionless situation, which way would the ramp go? Relative to the ground, which way would the ramp go? I'm seeing two different directions. So you're going, all right, Cheyenne, you're good with that?
Yep.
Okay. The trouble, and some people will do this with pins, and I've seen this, not saying that you did this in this particular case, but some people will go, it's gonna go that way. And I'm thinking, all right, which way? All right, so the ramp wants to shoot out that way. So friction is acting which way on the ramp?
Right.
It opposes it. So I got a friction going this way in a faded brown marker. So much better. One of these is gonna just really pop. Sure, we'll go with that. And
But R,
that's an R. Yes?
why there is a friction between the triangle and the ground?
Right? Why is there friction?
Yeah.
Because if the mass is heavy enough, in reality, this thing is gonna go shooting off. So the ramp, once it gets squirted, basically squirted out. Is that sufficient? Is that good enough?
Yeah.
Okay. Other questions at the moment? I can feel the excitement building. All right, so at this point, we've talked about, the four basic forces that we're dealing with in the beginning of the course. But we haven't done tension yet, so let's throw something with tension in. We'll make the ramp part of the ground, just to, some things are complicated enough. And have to introduce some magic here. The rope is an ideal rope. Sasson calls it a magic rope. Because an ideal rope has three characteristics. Characteristic number one, it is massless. So we are not worried about the weight of the rope itself. Number two, it is stretchless. So I'm not going to have one mass moving and the other mass is staying still. So it's not like a rubber band where I can have part of it moving and part of it not moving. And frictionless, I can still tie it off on something that it's got that kind of magic, but there's not going to be any friction between the rope and the pulley. For the duration of this course, the ropes will stay massless and stretchless. We might introduce friction, but it's not going to get too complicated. The pulley, right here, ideal pulley, it is massless and frictionless. In lab, we simulate the ideal pulley as best we can with, here they are, what are advertised as super pulleys, because they will spin for quite a while. The mass is not a whole lot there, so it comes close to massless, and this one seems to be wobbling a bit more than it should. As opposed to the old pulleys that we had, which stopped very quickly. Now, in terms of doing a force diagram here, there's clearly two boxes. There's a ramp part of the ground, but how about the pulley? Do I treat the pulley as a separate object or as part of one of the other objects? On the complex force diagram, I break it up for you so you don't have to go through that decision process. Some people will still, even though I'm trying to think of an exception to it, almost always will make the pulley part of whatever it's attached to. Some students still like to do forces between the pulley and the ground. Not necessary. Generally on the complex diagram, I'll circle it, and I'll write something like this, which is the symbol for ignore. That's IGN. Which means I don't take off for it, I just keeping track. So our objects, we have that. We call this box 1 and box 2. I have a rope. The pulley I'm making part of the ground, so the ground, ramp, and pulley are all one object. And I'm gonna redraw this, give myself a little bit more space. So I'm not changing anything structurally, if I've written it down, I'm just making it, giving myself room. Okay. And our checklist. Can we get rid, give people a chance to finish writing. Can we get rid of any of the forces? All right, because I did not introduce any mysterious force into the problem. All right. Where shall we begin?
Wait,
Okay, acting on what, which way?
there is weight between the box one and the ground.
Okay, which way is it acting on box one? Which way is it acting on box one? Somebody over there said it.
Down on the ground.
All right, so it's acting down on the ground?
Part of the ground, the ramp.
By angle arrow.
All right, sorry, we're doing weight, aren't we? Weight, was that what was, okay. Which way does weight act on objects?
Down.
Yep, down is defined actually by the way the weight acts. Weight is straight down. Doesn't matter what else, if the ramp disappeared, that still exists and is acting straight down. But they come in pairs. Now, I drew it over here, it's on the ground somewhere. You know, if you want to draw the arrow here, like it's part of this ramp, that's fine too. All right, we're good with this? I got a subtle nod over there, I got two nods, all right.
Well, also on the other box. On the other box, downwards. And then up from the ground. I guess we can do 1 and 2.
All right. We need subscripts on at least one of them. All right, so weight is done, I have only two. The rope is massless, so it has no weight. And so I have only two objects with mass besides the planet, so weight is done. Next. I will say, let's save friction for last.
There's natural, force.
Ooh, the most common mislabel. Not natural.
Oh, normal, sorry.
Yes, there we go.
Normal acting up on the first box, and then,
Acting up.
well, it's between the ramp and the box.
Okay, I agree with that. Which way is it acting on the box? I think somebody over there said it. I see a hand gesture. So that way or that way? Normal force is a pushing force. It's pushing it away. So you've got this normal force here.
And then down on the ramp,
I assume you mean at an angle.
yes.
Was this your intent when you originally said up on the box?
Yeah.
Okay. All right, so we have contact there.
Same on box 2,
What is box 2 touching?
the ramp. So
It is not touching the ramp.
Oh.
If it were, I have had problems where that mass is touching the ramp, in which case you'd have, pair of forces like that, or whatever subtle angle it is. But in this problem, 2 is not touching the ramp. But there is another pair of normal forces.
Back to 2 don't touch the ground, so there is no
It's
normal.
not touching the ground either. Because we're doing a force diagram at this moment in time. We're not projecting the future.
Is it the roof?
And,
Both boxes.
all right, so the force between the rope and the boxes, we actually not quite sure how it is attached. Is there an eye hook and it's attached to the eye hook, in which case there's a normal force there? Or is it sort of wedged inside like that, in which case friction is it? Since we don't know how it's attached, we're gonna call that tension.
Okay.
So tension's sort of a catch-all. I've heard some physics instructors say tension doesn't really exist. And what they mean is that tension is really one of the other forces, but when we don't know, we lump it into tension. But there is another pair of normal forces you had, and it does involve the rope.
The rope and the pulley?
Yes. Now, I don't know the exact angle. The rope starts touching at this point and it stops touching there, so the normal force is somewhere in that range right there. And so I just sort of split the difference and got some normal force there, some normal force back. We do need to make a small adjustment to what I've written up here. Doesn't change what I've written. But what do we need to do in order to make this?
2.
You said 2?
Yeah.
If you don't like 2, then you should have spoken up before Cheyenne. The other one we can keep as Y, just so long as it's different. Personally, I put the subscripts in there, but if there's no call for it, then we don't need to. Just so long as these are different here. All right, I think that's it for contact. So normal force is done. And then tension. You need to flash back to your notes about directions of tension.
Towards each other.
Right, they are towards each other. It's a pulling force. Pulling forces are towards each other. Weight is a pulling force. Tension is a pulling force. All right, so which way is it acting on, let's say, box 1? All right.
Angle go up.
So we have this tension here. It comes in pairs. Where's the other part of that force?
From the roof, go down.
And it should be parallel to the rope. So it's
Then there is between back to 2 and the rope,
absolutely,
the opposite. From the rope go down,
yes.
and from the back to go up.
All right.
I
Okay, subscripts. If it is an ideal rope, then we can assume that these tensions are the same. In an ideal rope, these tensions will be the same. If you throw friction into it, if there's friction between the rope and the pulley, these tensions will not be the same, but it is. So for a single rope, not having subscripts here is not, it's fine. If I have a second rope, then you need to have subscripts. But with only a single rope, you don't need them. But if you do put in subscripts, these two have to have the same subscript. These two have the same subscript. So 1, 1, 2, 2. But just emphasizing optional if only one rope, one ideal rope. And I'm sure on video that can be read incredibly clearly. That should be a little bit better. No harm, if you put them in there, and some students do, and there's no penalty for that, it's perfectly fine. Slightly more accurate. But when we did the rope in the hallway bit, one of the things I said was that the force that, I'm trying to remember who was pulling on the sides. Oh, you were in the middle? Whoever was on the sides, Rachel and Carrie, that they were basically exerting the same force on each other. It's not like the force weakened as it went towards the middle. They were basically pulling on each other with the same force. And this is what I was keeping in mind. Now, as Manal pushed on it, potentially there could be some variation depending on how close she was to the middle. All right, so tension is done because I have only one rope and I've got my pairs at each end. Tension done. Friction. Friction is going to act between what two objects?
And the ramp.
Okay, which way will it act? Okay. On the box, is it going to go up the ramp or down the ramp?
Up the ramp.
Anyone want to disagree with that?
Down the ramp.
All right, there we go.
Oh,
You just wanted to say something different, Cheyenne, or?
I was just, I don't know.
on the box,
Yeah.
upwards, like at an angle.
All right.
We're wording crazy.
Now, I mean, I'm not questioning the wording, I'm questioning which way, if this is a frictionless situation here, and I let go, which way is the box one gonna go, or which way is box two gonna go?
Downwards.
Box one's gonna go downwards? So is the system, let's see my hand-eye coordination here, is it gonna do this, or is it gonna do that?
It depends on the weight of the boxes.
And the angle. What are the relative masses? What is the angle here? Now, if in 151 and 251,